It's hard to think of a hotter topic than deep learning, and that's what we're going to talk about in depth and hands-on for the next few hours. I'm going to show you how neural networks work, artificial neural networks, perceptrons, multi-layer perceptrons, and then we're going to talk into some more advanced topics like convolutional neural networks and recurrent neural networks. None of that probably means anything to you right now, but the bottom line is if you've been curious about how deep learning and artificial neural networks work, you're going to understand that by the end of these next few hours. So think of it as deep learning for people in a hurry. I'm going to give you just enough depth to be dangerous, and there will be several hands-on activities and exercises so you can actually get some confidence in actually applying these techniques and really understanding how they work and what they're for. I think you'll find that they're a lot easier to use than you might have thought. So let's dive in and see what it's all about. This section of my larger machine learning and data science course is actually available as a standalone course as well. So if you are new to this course here, you are going to need to install the course materials and a development environment if you want to follow along with the hands-on activities in this deep learning section. If you are new, just head on over to sundog-education.com/machine-learning. Make sure you pay attention to the dashes and the capitalization. It all matters, and don't spell anything wrong. And you should get to this page here. You'll find here a handy link to the course materials. Just download that and decompress it, however you do that on your platform, and remember where you put it. If you want to join our Facebook group, you can. It's totally optional, just a place for students to hang out with each other. And our development environment for this course will be Anaconda, which is a scientific Python 3 environment. You can install it from here. It is free software. Make sure you install the Python 3.7 or newer version. Once you've installed Anaconda, you'll need to install the TensorFlow package. So on Windows, you would do that by going to the Anaconda prompt. So go to Anaconda in your start menu and open up Anaconda prompt. On Mac OS or Linux, you would just go to a terminal prompt and it would be all set up for you already. From there, you would type in conda install TensorFlow and let that run to install the TensorFlow framework that we will use within Anaconda. If you have an NVIDIA GPU, you might get better performance by saying TensorFlow-GPU, but sometimes that results in compatibility issues. So don't do that unless you know what you're doing, guys. You do not need to install Py.Plus for this particular section of the course. Can't hurt to do it, though. That's also part of the setup instructions for the larger course. And you also need to understand how to actually start the notebooks once you have them installed. So from that Anaconda prompt, that same Anaconda prompt that we talked about earlier, to actually launch one of the notebooks in this course, you would first change your directory to wherever you installed the course materials. So for me, I put them in C:\ml course. And if I do a dir, you'll see all the course materials are here. From here, if I type in Jupyter Notebook, and Jupyter is spelled funny with a Y, that should launch your web browser with a directory of all the different notebooks that are a part of this course. So when I say in this course to open up, for example, TensorFlow.ipynb, the TensorFlow notebook, you would just scroll down to this list, open up TensorFlow.ipynb, and up it should come. When you're done experimenting and playing around with this notebook, you can just go to File, Close, and Halt to get out of it. And when you're done with Jupyter entirely for this session, just quit, and that will shut everything down for you. All right, so with that out of the way, let's move on. Let's talk about some of the mathematical prerequisites that you need to understand deep learning. It's probably going to be the most challenging part of the course, actually, just some of the mathematical jargon that we need to familiarize ourselves with. But once we have these basic concepts down, we can talk about them a little bit more easily. I think you'll find that artificial intelligence itself is actually a very intuitive field. And once you get these basic concepts down, it's very easy to talk about and very easy to comprehend. First thing we want to talk about is gradient descent. This is basically a machine learning optimization technique for trying to find the most optimal set of parameters for a given problem. So what we're plotting here basically is some sort of cost function, some measurement of the error of your learning system. And this applies to machine learning in general, right? Like you're going to have some sort of function that defines how close to the result you want your model produces results for, right? So we're always doing, in the context of supervised learning, we will be feeding our algorithm, our model, if you will, a group of parameters, some sort of ways that we have tuned the model. And we need to identify different values of those parameters that produce the optimal results. So the idea with gradient descent is that you just pick some point at random, and each one of these dots represents some set of parameters to your model. Maybe it's, the various parameters for some model we've talked about before, or maybe it's the exact weights within your neural network. Whatever it is, we're going to try some set of parameters to start with. And we will then measure whatever the error is that produces on our system. And then what we do is we move on down the curve here, right? So we might try a different set of parameters here, again, just sort of like moving in a given direction. with different parameter values, and we then measure the error that we get from that. And in this case, we actually achieved less error by trying this new set of parameters. So we say, okay, I think we're heading in the right direction here. Let's change them even more in the same way. And we just keep on doing this at different steps until finally we hit the bottom of a curve here, and our error starts to increase after that point. So at that point, we'll know that we actually hit the bottom of this gradient. So you understand the nature of the term here, gradient descent. Basically, we're picking some point at random with a given set of parameters that we measure the error for, and we keep on, pushing those parameters in a given direction until the error minimizes itself and starts to come back up to some other value. Okay, and that's how gradient descent works in a nutshell. I'm not going to get into all the hardcore mathematics of it all. The concept is what's important here, because gradient descent is how we actually train our neural networks to find an optimal solution. Now you can see there are some areas of improvement here for this idea. First of all, you can actually think of this as sort of a ball rolling downhill. So one optimization that we'll talk about later is using the concept of momentum. You can actually have that ball gain speed as it goes down the hill here, if you will, and slow down as it reaches the bottom and, kind of bottoms out there. That's a way to make it converge more quickly when you're doing things, and that can make actual training your neural networks even faster. Another thing worth talking about is the concept of local minima. So what if I randomly picked a point that ended up over here on this curve? I might end up settling into this minima here, which isn't actually the point of the least error. The point of the least error in this graph is over here. That's a problem. That's a general problem in gradient descent. How do you make sure that you don't get stuck in what's called a local minima? Because if you just look at this part of the graph, that looks like the optimal solution. And if I just happen to start over here, that's where I'm going to get stuck. Now, there are various ways of dealing with this problem. Obviously, you could start from different locations to try to prevent that sort of a thing. But in practical terms, it turns out that local minima aren't really that big of a deal when it comes to training neural networks. This just doesn't really happen that often. You don't end up with shapes like this in practice. So we can get away with not worrying about that as much. That's a very important, good thing, because for a long time, people believed that AI would be limited by this local minima effect, and in practice, it's really not that big of a deal. Another concept we need to familiarize ourselves with is something called autodiff. And we don't really need to go into the hardcore mathematics of how autodiff works. We just need to know what it is and why it's important. So when you're doing gradient descent, somehow you need to know what the gradient is, right? So we need to measure what is the slope that we're taking along our cost function, our measurement of error, or it might be mean standard error for all we know. And to do that mathematically, you need to get into calculus, right? If you're trying to find the slope of a curve and you're dealing with multiple parameters, and we're talking about partial derivatives, right? The first partial derivatives to figure out the slope that we're heading in. Now, it turns out that this is very mathematically intensive and inefficient for computers to do. So by just, doing the brute force approach to gradient descent, that gets very expensive very quickly. Autodiff is a technique for speeding that up. So specifically, we use something called reverse mode autodiff. And what you need to know is that it can compute all the partial derivatives you need just by traversing your graph in the number of outputs plus one that you have. And this works out really well in neural networks, because in a neural network, you tend to have artificial neurons that have very many inputs, but probably only one output, or very few outputs in comparison to the inputs. So this turns out to be a pretty good little calculus trick. It's complicated. You can look up how it works. It is pretty hardcore stuff, but it works, and that's what's important. And what's also important is that it's what the TensorFlow library uses under the hood to implement its gradient descent. So again, you're never going to have to actually implement gradient descent from scratch or implement autodiff from scratch. These are all baked into the libraries that we're using, libraries such as TensorFlow for doing deep learning. But they are terms that we throw around a lot, so it's important that you at least know what they are and why they're important. So just to back up a little bit, gradient descent is the technique we're using to find the local minima of the error that we're trying to optimize for, given a certain set of parameters. And autodiff is a way of accelerating that process so we don't have to do quite as much math or quite as much computation to actually measure that gradient of the gradient descent. One other thing we need to talk about is softmax. Again, the mathematics aren't so complicated here, but again, what's really important is understanding what it is and what it's for. So basically, when you have the end result of a neural network, you end up with a bunch of what we call weights that come out of the neural network at the end. So how do we make use of that? How do we make practical use of the output of our neural networks? Well, that's where softmax comes in. Basically, it converts each of the final weights that come out of your neural network into a probability. So if you're trying to classify something in your neural network, like, for example, decide if an image is a picture of a face or a picture of a dog or a picture of a stop sign, you might use softmax at the end to convert those final outputs of the neurons into probabilities for each class. Okay, and then you can just pick the class that has the highest probability. So it's just a way of normalizing things, if you will, into a comparable range, and in such a manner that if you actually choose the highest value of the softmax function from the various outputs, you end up with the best choice of classification at the end of the day. So it's just a way of converting the final output of your neural network to an actual answer for a classification problem. So again, you might have the example of a neural network that's trying to drive your car for you, and it needs to identify pictures of stop signs or yield signs or traffic lights. You might use softmax at the end of some neural network that will take your image and classify it as one of those sign types, right? So again, just to recap, gradient descent, an algorithm for minimizing error over multiple steps. Basically, we start at some random set of parameters, measure the error, move those parameters in a given direction, see if that results in more error or less error, and just try to move in the direction of minimizing error until we find the actual bottom of the curve there, where we have a set of parameters that minimizes the error of whatever it is you're trying to do. Autodiff is just a calculus trick for making gradient descent faster. It makes it easier to find the gradients in gradient descent just by using some calculus trickery. And softmax is just something we apply on top of our neural network at the very end to convert the final output of our neural network to an actual choice of classification, given several classification types to choose from. Okay, so those are the basic mathematical terms or algorithmic terms that you need to understand to talk about artificial neural networks. So with that under our belt, let's talk about artificial neural networks next.